And we're going to start discussing chapter 6, which is a very, very interesting chapter from a theory perspective, because it really helps you understand how reactions function. So hopefully you remember your kinetics from 102, as this is where it's finally going to pay some dividends. So first and foremost, let's just discuss general features of molecules. So polarizability is the tendency to undergo polarization. Polarization is a change in electron distribution in a bond or molecule as a response to the change in the electronic nature of the surrounding atoms. So for example, we know that a carbon attached to an electron withdrawing group will develop a partial positive charge. Okay? Polar reactions can occur between regions of high electron density, delta minus, and regions of low electron density, delta plus. We call electron deficient species electrophiles, electron-loving species. They're an electron-poor species. A Lewis acid is a common example of an electrophile. So for example, ketone groups are electrophilic at the carbon position. Alkyl chlorides are electrophilic. Vinyl ketones are electrophilic at two positions, the beta position and the ketone carbon. Bromine is electrophilic. We can think of it as one bromine having a building positive charge and one bromine having a building negative charge. Hydrochloric acid, the acidic proton is electrophilic, so H plus is an electrophile. And carbocations are electrophilic. In this case, we have a formal positive charge. So anytime you see a region that's electron deficient, that has a partial positive or formal positive charge, it can behave potentially as an electrophile. So electrophiles react with nucleophiles, nucleophile, nucleus-loving molecules in polar reactions, and electrophiles prefer, so electrophiles, their main feature is that they accept electron density in lone pairs. Now, what do I mean by nucleophile? Nucleophiles are an electron-rich species. A Lewis base is an example of a nucleophile. So in this case, for example, we call this species an enolate. It has a partial negative charge at multiple carbons. Alkenes can also be thought of as nucleophiles because this is a very electron-rich pi bond. In this case, for alkoxides and other anions, we have a formal negative charge. Remember, our organometallics are overwhelmingly nucleophilic species because you can really think of this organometallic as having our lone pair almost exclusively centered on the carbon, because it's not really a formal bond. This is an ionic bond. It's an ionic interaction between our metallic species and our carbon atom. And other anionic species can also be thought of as nucleophiles. So nucleophiles, you think partial negative to formal negative charge. Does that make sense so far? Is everyone comfortable with our definitions of nucleophile and electrophile? Any questions on that? Okay, let's keep going then. So let's look at some common polarity patterns in functional group. This is a nice little way of checking your work, and I'd also recommend that you review chapters 1 and 2 in terms of assigning electron-rich and electron-deficient atoms in molecules. This will help you recognize patterns of reactivity. You can always have that as a reference in your notes. Now, let's look at this idea that molecules can have electrophilic and nucleophilic sites. So as we discussed previously, electrophilic sites are electron deficient, so delta plus, while nucleophilic sites are electron rich, delta minus. So to determine the distribution of electron density, we'll look at the partial charge of each atom, considering number 1, resonance contributions. So in this case, when we think about our ketone functionality, we have a major resonance structure where there is a positive partial charge on our carbon. So we'd expect this carbon, for our ketone carbon, to be electrophilic. Let me not draw it as an arrow. And we'd expect the ketone oxygen to be slightly nucleophilic. Likewise, if we're looking at an enamine, we have a major resonance contributor where the rightmost carbon has a formal negative charge. So we'd expect that we'd build up some negative charge on this carbon here. And because this nitrogen has a lone pair, even though it has a positive charge in the resonance structure, this nitrogen still is relatively electron rich because this resonance contributor is relatively small. And it still has electron density from this double bond. Now, if we wanted to draw another resonance structure for this enamine, we could potentially kick our lone pair back up to the nitrogen and draw a resonance structure that looks a little bit like this. And now from this resonance contributor, what can we say about the central carbon of our enamine? Would we expect our central carbon of our enamine to be nucleophilic or electrophilic in character? Would we expect it to have a partial positive or partial negative character? So looking at our central carbon in all of our resonance contributors, do we see it have a lot of, oh yeah. Okay, perfect. So yes, everyone agrees that this center would be electrophilic, and our central carbon of our enamine has a partial positive character. Now, in addition to resonance effects, inductive effects also can play a huge role. For inductive effects, atoms bonded to more electronegative atoms are electron deficient. Let me color code that more appropriately. So atoms bonded to more electronegative atoms or electron withdrawing groups are electron deficient, while atoms bonded to less electronegative atoms are electron rich. So for example, if we think about a carbon-boron bond, what atom is more electronegative, carbon or boron? And this will be important later. What's more electronegative, carbon or boron? Carbon, right? So carbon has a delta minus, boron has a delta plus. Okay. If we compare and we look at a carbon-chlorine bond, which atom is more electronegative, carbon or chlorine? Chlorine, right? So we'd expect carbon to have a partial positive or an electrophilic character. Just like if we look at a carbon-sulfur bond, the carbon and the hydrogen would have electrophilic character. Okay, now this is a really cool example. This is really cool. If we look at a nitrogen-bromine bond, now let's take a moment and let's think about this really carefully. Would we which atom would you expect to have to be more electron withdrawing, nitrogen or bromine? And I'll give you a hint. This reagent is thought of as a source of Br+. So what's more electron withdrawing? Nitrogen or bromine? Nitrogen, yep. It's polarized like so. So always keep in mind inductive effects, because you need to identify nucleophilic and electrophilic sites in order to predict patterns of reactivity. That's the skill we're trying to develop. So your goal, and essentially the whole point of this exercise, is to be able to look at a molecule and say, this is nucleophilic, this is electrophilic, this is how our molecule can react. Okay, so let's try to put these concepts together. Let's try to put these concepts together and apply these concepts to the following problem. So let's try to indicate atoms that are electron deficient and electron rich in the following structure. So I'll do this first one and then you'll tackle the second one. So I'm going to draw out some resonance contributions. I'm going to draw out some of my resonance contributors. So first I'm going to kick this lone pair up. That's perfectly allowable in terms of resonance structures. It's not a very major resonance structure, but it can give me some insights here. Oftentimes when you're assigning nucleophilic and electrophilic centers, you're not as concerned with the dominant resonance structures as the second most dominant. We're going to kick the lone pair down and we're going to draw the following resonance contributor. Okay, so with that all established, my question to all of you is, if we look at our molecule, which sites are electron rich? What sites are electron rich by resonance and by induction? What sites are electron rich? What sites do we see a partial negative charge? The oxygens, exactly right. Okay, what other sites are nucleophilic? Actually, we finished all of our nucleophilic sites. What site is electron deficient? What site is electron poor? The carbon, yep, exactly right. Perfect, so we've identified our electron deficient and our electron rich sites. Let's do one more together, as this one's pretty interesting. So looking at the following molecule, if we think about a carbon-phosphorus bond, which atom is more electron withdrawing, carbon or phosphorus? Which atom is more electron withdrawing? Which atom is more electron negative, carbon or phosphorus? Carbon, yep. Carbon is actually slightly more electronegative than phosphorus. So if we think about our resonance structures, a major resonance structure for this type of reagent, known as a Wittig reagent, would be something like this. So then, thinking about the polarizability of our bonds, which site is most nucleophilic? Which site gets a delta minus? Which site is electron rich? The carbon or the phosphorus? What site's electron rich in this case? So if we draw our molecule out, which site is electron rich? The carbon. So it has a delta minus. Well, our phosphorus is relatively electron deficient. So it has a delta plus. Identifying sites that are electron rich and electron deficient will help you logically pace through reactions you may not have seen before. So this is building the fundamental skills to draw reaction mechanisms. So with that established, let's now take a look, and I'd like you now to assign the sites that are electron rich and electron deficient in the following molecule. And I'll put some letters here. So A, B, C, D, E. And I'd like you to tell me which sites are electron deficient and which sites are electron rich. So take about 2 to 3 minutes to work through that problem, and we'll come together as a group to discuss. So would anyone like to provide insight into which sites are electron deficient or electron rich? Don't be shy to communicate in the chat. I want to see a few responses before we talk through this problem. Okay, so we have a good pool of answers. Let's work through each of these problems, and let's start by drawing out some resonance structures. So it's good that we have disagreeing answers between all of our responses. That's always good. So let's draw our first resonance structure, where I'm just going to kick this double bond up to oxygen. Okay, in our second resonance structure, I'm going to kick this double bond to our site that's electron deficient. Okay, so looking at our resonance contributors now, and looking at our overall structure, let's start by identifying which sites are electron rich. Oh, whoops, sorry, one moment. Let's draw one more resonance contributor as well. Let's draw one more resonance contributor where we kick this lone pair down and our double bond electrons get displaced, and we end up with the following structure. Okay, perfect. We now have all of our resonance structures in place, and let's identify all the sites that are electron rich, that have a clearly defined partial negative charge in one of the resonance structures. So I see a lot of people mentioning C. That's exactly right. Are there any other sites that are electron rich? Any other sites that are electron rich? D, exactly right. Now let's identify our electron deficient sites. Let's identify our electron deficient sites. So what sites do we observe a partial positive charge? What sites do we observe a partial positive charge? I see B and E, that's exactly right. Yep, perfect. So we've assigned all the sites that are electron rich and all the sites that are electron deficient in the following molecule. This is a useful way of looking and identifying sites of potential reactivity. You can, however, you'd want to place the positive charge as far as possible away from your electron withdrawing group. You don't want to have a positive charge directly adjacent to a withdrawing group, as that destabilizes that positive charge. Does that make sense? Yeah, perfect. So let's keep going through these examples, and let's talk a little bit about organic mechanisms. So organic reactions occur through bond forming and bond breaking steps. These are the fundamental principles behind reactions. So mechanisms serve to describe the movement of electrons in bond forming and bond breaking steps in a chemical reaction. So some bond forming and bond breaking events are concerted, which means the bond breaking and bond forming steps occur simultaneously. So a classic example of a concerted reaction is the SN2 reaction, where the bond formation and bond breaking steps occur in a single step. So we have our attack and leaving of our, the attack of our nucleophile and the loss of our leaving group in one step. So this process is concerted. The alternative to a concerted reaction is what's known as a stepwise reaction. So stepwise reactions, the bond breaking and bond forming steps occur in separate steps of the mechanism. So an example of a stepwise reaction would be the SN1 reaction, where the bond formation and bond breaking occurs over multiple discrete steps. So we have a step 1 where the leaving group leaves, and then a step 2 where your nucleophile attacks. So just pay special attention to whether a reaction is indicated as concerted or stepwise. So just be wary, those terms have special weight with regard to the mechanism. Okay, so we indicate the movement of electrons in chemical reaction mechanisms using curved arrow notation, similar to how we indicated the movement of electrons in in resonance structures. So we're next going to talk about types of reactions. So polar reactions involve heterolytic and unsymmetrical bond forming and bond breaking events. So for polar reactions, we're primarily going to be looking at two electron movements. So to describe the movement of two electrons, we use what's known as a double-headed arrow. Okay? So for example, in acid-base reactions, if we look at the movement of this lone pair, which is two electrons, to form a new bond, we draw it with a double-headed arrow. So this is very similar to what we've seen in acid-base chemistry. Okay, so the curved arrow for bond formation is drawn from the lone pair or source of electron density, such as a pi bond, to the second atom that's part of the new bond. The arrow is drawn from the nucleophilic lone pair or nucleophilic bond to the electrophilic center. So for example, if we're drawing the attack of an alcohol on a carbocation, we draw our arrow going directly from our lone pair to our electrophilic atom. Does that make sense to everyone? Does everyone see the movement of electrons and how that correlates with a bond forming event? Is everyone comfortable with this idea so far? Okay, so let's talk a little bit about bond breaking events. The curved arrow for bond breaking is drawn from the bond between the two atoms to the atom receiving the lone pair or electron density. So if we're breaking our bond asymmetrically, this arrow is saying that our two electrons move to chlorine. So we generate a carbocation and an anion. Okay, so this kind of movement of electrons is commonly seen in heterolytic bond cleavage, also known as polar or asymmetrical bond breaking. So in heterolytic bond cleavage, the electrons shared between two atoms are distributed to one atom during bond breaking. So does everyone notice how the bromine receives two electrons from the bond? We have broken our bond and our electrons are going only to the bromine. That's why carbon has a positive charge, because it no longer has those shared bonding electrons. So like polar bond breaking, where we have a movement of 2 electrons, and those 2 electrons are given to one of our atoms or one of our species in our bond. In polar bond formation, the 2 bonding electrons are donated by 1 reactant. So for example, in this case, our nucleophile, which I'll write in blue, our nucleophile donates 2 electrons, and our electrophile receives those electrons as we form the bond. Okay, so polar bond breaking and bond forming involves asymmetrical bond forming and asymmetrical bond breaking events. It's the movement of 2 electrons. Okay. So let's suppose we want to signify the movement of just a single electron. Well, to signify the movement of a single electron, we use half arrow notation. So this is our half arrow. So half arrow notation is commonly used for what I'd like to call radical reactions. So radicals are species with an incomplete octet and an unpaired electron. So the main way that we generate radicals is via homolytic cleavage, where we have symmetrical bond breaking, where the electrons in the bond are evenly distributed to the 2 atoms as the bond is broken. So does everyone notice each bromine atom in this bromine-bromine bond receives 1 electron? So we make 2 bromine radicals. Does that make sense to everyone? Does everyone see the difference between heterolytic and homolytic cleavage? Okay. So in symmetrical bond formation, the half arrow is drawn from the bond or radical contributing the electron to the location of the new bond formed. So in this case, if we have a radical from our bromine and our carbon, so each atom is contributing 1 electron to form a carbon-bromine bond. This is where our 2 electrons ended up. Notice we use half arrow notation for each of our 1 electron movements. So if we're looking at symmetrical bond breaking, the 2 half arrows are drawn from the bond to each atom participating in the bond. So each of these half arrows represents the movement of 1 electron. Okay, let's talk a little bit about how we can put these ideas together to generate some more complex ideas. So we're next going to delve into radical reactions, and we're going to look at some radical reactions in detail. How do radical reactions function? Well, all radical reactions are started off by what's known as an initiation step, where 2 radical species are formed by homolytic bond cleavage. So we're breaking our bromine-bromine bond. Also, if you have peroxides, which are the form ROOR, you can also subject peroxides to heterolytic bond cleavage to generate peroxy radicals. That's also a valid way of initiating many radical reactions. Now, one measure that we use to assess the energy required to break a bond in a heterolytic fashion is the bond dissociation energy, which is the amount of energy required to break a given bond to produce 2 radical fragments when the molecule is in the gas phase at 25 degrees Celsius. So bond dissociation energy essentially describes the energy required to heterolytically break a bond. You should have seen bond dissociation energy in 101 or 102, your general chemistry sequence. And we'll be talking a little bit about bond dissociation energy and how it relates to chemical reactions in organic. Here is a table of bond dissociation energies for your reference, as we're going to use these bond dissociation energies to calculate and estimate the enthalpy of a reaction. Okay, so let's show how that works out in practice. Now, the next step in a radical reaction is propagation, which is reaction of a radical with another molecule to yield a new radical. So propagation can occur either by abstraction, where an atom is removed from a molecule to yield a new molecule and a new radical. So in this case, our bromine radical abstracts a hydrogen from methane. And in turn, we generate a new molecule and a new radical. Propagation can also occur in an additional process via addition, where the radical adds to an alkene to yield a new radical. So let's redraw this below. So we have our radical and we have our alkene. We're forming a new bond and a new radical. So these are the two ways where propagation can occur. And the key thing I want you to keep in mind, propagation can repeat multiple times with different pairs of molecules. So just as easily you can have your radical generated from this earlier step. You can have it abstract a hydrogen from any species. You can have it add. You can have it abstract from an entirely different molecule in your reaction mixture. Radical reactions can propagate in a variety of ways. So here's another example of propagation via abstraction. Now, eventually, the radical chain process will undergo termination, where two radicals react to generate a stable product. So in this case, just to redraw it once again, we have our methane-based radical reacting with our bromine radical, one electron movement each to form a carbon-bromine bond. So we call this process termination, as we no longer have our two radicals present. We've terminated our radical chain. This species is no longer a radical, so it can't further propagate the chain. Does that make sense to everyone so far? Is everyone comfortable with this idea? Radicals are unstable, so they will readily abstract, add, or terminate to get rid of that radical character. Most radicals are high energy species, and they readily react to generate lower energy species. But this molecule can just as easily react with another radical and reinitiate a new chain. But that typically you don't often see repeated reinitiation for bromination in particular. Usually you observe a fair amount of selectivity for monobromination, and we'll talk about why that is actually. So let's look a little bit at the reactivity and the relative reactivity of alkyl CH bonds in radical reactions. So the key feature I want you to keep and be aware of is that radicals are stabilized by adjacent bonded non-hydrogen atoms. So in terms of radical stability increases as we go from methyl to a primary, secondary to a tertiary. So as we notice, if we look at the bond dissociation energy, or the BDE value, as we notice, our strongest bond for our carbon-hydrogen bond occurs when we have the least stable radical. The weakest carbon-hydrogen bond occurs when we have the most stable radical. So one thing that we can take away from our radical stability discussion is that the most reactive carbon-hydrogen bond to abstraction generates the most stable radical. This is something that we can see just experimentally. Now, we can also look at other types of radicals, such as allylic radicals. So these radicals, or radicals in general, can be stabilized by adjacent pi systems via resonance. So if we look at our carbon-hydrogen bond dissociation energy for our tertiary carbon-hydrogen bond, we see that a tertiary radical is relatively stable. However, an allylic radical, we call this an allylic radical, is even more stable because this radical can be dissociated through our pi system via resonance. Can be dissociated through our pi system via resonance. So we can draw the following resonance contributor. And we can clearly see that this radical is stabilized by resonance. And the more resonance delocalization we have, the more stable our radical becomes. So if we have a doubly allylic species, we have an even more stable radical and an even weaker carbon-hydrogen bond. Does that make sense so far? Do these trends match with what we observed previously when we talked about, for example, anion stability or cation stability? Okay, so let's try to explain this idea. Why are radicals stabilized by adjacent groups? Well, hyperconjugation is this idea where we have an overlap of a p orbital with an adjacent sigma bonding molecular orbital. So we have our p orbital and it's overlapping with our sigma bonding molecular orbital. Now, as a result of this hyperconjugation, as a result of this overlap, we end up with donation of electron density into p orbital, and we end up stabilizing our p orbital. So this overlap, this orbital overlap, delocalizes our electron density about a greater number of atoms, and it stabilizes this p orbital via electron donation. So the more adjacent sigma bonding MOs we have, the greater the effect of hyperconjugation, because we have more opportunities, more sigma bonds that it can overlap with our p orbital and donate electron density. So hyperconjugation of adjacent sigma bonding molecular orbitals stabilizes the radical in our p orbital. Radicals are electron deficient species, so donation of electron density into the p orbital via hyperconjugation stabilizes our radical. So this matches our general trend that radicals are stabilized by increasing substitution. That's why tertiary is more stable than secondary, which is more stable than primary. Because we have a greater number of adjacent sigma bonding molecular orbitals that can engage in hyperconjugation. Does this idea make sense to everyone? The presence of adjacent sigma bonding molecular orbitals in turn overlaps with our p orbital and stabilizes our electron deficient radical. You can think of it as a relative to this idea of pi bonding, but it's not like a formal bond. It's just a weak orbital overlap that results in sharing of electron density into our p orbital. So it's not like a formal bond. It's just an overlap of electron density that results in donation of electron density into our p orbital. But it's not like a formal bond. Not necessarily. As long as there is an adjacent sigma bond, then it's able to stabilize via hyperconjugation. As long as there's an adjacent sigma bond, it's able to stabilize our p orbital via hyperconjugation. Okay, so this explains our stability trend for radicals. So to explain and to tackle this idea of allylic substituents, let's take a look at some allylic substituents. One moment. Let me just zoom in really quickly. Okay, so an allylic substituent is located on the whoops, sorry about that. Sometimes Zoom lags a little bit. An allylic substituent is located on a carbon adjacent to a carbon-carbon double bond. So all three of these hydrogens would be called allylic hydrogens. Now, allyl radicals are stabilized via resonance, and as a result, the allylic CH and CX bonds have lower bond dissociation energies than expected. So we can see this based on the fact that we can dissociate and stabilize our radical via resonance. So to draw an orbital picture of what's going on here, so we have our sigma bond. And we have our pi bond, and the radical is being held in a p orbital that in turn can be dissociated throughout our pi system. So essentially we're distributing our radical character throughout all of our carbon atoms, which is stabilizing this electron deficient carbon. So the radical is being held in an empty p orbital. Just like what we saw with resonance stabilization of anions, for example. So that makes sense as to why it's relatively easy to generate allylic radicals, because they're stabilized via resonance and they're relatively low in energy. Okay. Let's talk a little bit about radicals and substituent effects. So radicals can adopt what's known as a shallow pyramid geometry, allowing the half-filled p orbital to interact with adjacent p orbitals and pi bonds. So radicals can be delocalized via resonance through the overlap of the radical containing p orbital and the adjacent pi system. So this explains why allylic radicals are more stable than vanillic radicals. So this is our allylic radical, which we can very easily see we can delocalize across multiple atoms via resonance. And if we compare that now to our vanillic radical, what orbital is this vanillic radical being held in? What orbital is this vanillic radical being held in? Let's think about that for a moment. Yeah, it's being held in an sp2 orbital. So can we easily delocalize this vanillic radical? Can we easily delocalize and stabilize this vanillic radical? No, we can't, because it's in an sp2 orbital. It's not in a p orbital. It can't be delocalized via conjugation to any pi system. It's just locked on our carbon atom. Exactly right. So we also can have other substituent effects. So atoms with lone pairs adjacent to a radical can stabilize radicals by donation of electron density. And I'd like you to recall that resonance donors are more efficient donors if they are less electronegative and can accommodate a positive charge more readily. So for example, if we look at a radical, so for example, if we look at the CH2 radical, yes. Yes, do you have a question?
It's just easier to say without tapping. When we were talking about the orbital for, yeah, right above, it's sp2 because the radical itself counts as a group?
Yes.
Okay.
Mm-hmm. Yeah. Perfect. So let's talk about the idea of substituent effects. If we have an amine adjacent to our radical, this amine can delocalize our radical via donation of electron density. So we can delocalize our radical via resonance, and we can generate a structure that looks something like this. So in effect, we're distributing our radical character across multiple atoms, and we've donated some electron density into our radical. The same thing occurs if we have an adjacent alcohol. Would someone like to comment as to why an alcohol is a less efficient donor? Is this alcohol more or less electron withdrawing? Is our alcohol more or less electron withdrawing than a nitrogen? More, right? So we have a small electron withdrawing effect, but we have a substantially larger resonance effect. And the resonance stabilization wins out over the electron withdrawing character. That is why if we notice and we compare just like a CH in CH3 to a CH bond where we have an adjacent fluorine, even fluorine can contribute to this behavior. Even fluorine can participate and exhibit a donation effect. So the donor effect wins out over the withdrawing effect. Does that make sense to everyone for radical stability? Is everyone comfortable with that idea? That it's resonance donation. Radical stability increases when you have adjacent lone pair donors. Okay. So let's look at radicals and atom effects. So radicals are electron deficient species and they're destabilized when they're placed on an electronegative atom. So for example, if we compare carbon, nitrogen, oxygen, and fluorine, so fluorine is our most electronegative. So fluorine is our most electronegative, and that's why it has the least stable radical. So one way you can think about it is that radical stability decreases from left to right along the periodic table as electronegativity increases. Okay. Additionally, in terms of atom effects, radicals are more stable on larger atoms as the electron is placed farther from the nucleus and the electron density is distributed over a larger area. This is the exact same type of atom effect that we observed when we discussed anion stability. So radical stability increases going down the periodic table as we can distribute our electron density over a larger orbital area. That's why as we go from fluorine to iodine, we see we have a larger atom, which in turn means we have a more stable radical. Any questions so far in terms of our trends for radical stability? Is everyone good so far? Any questions? Okay. So let's talk a little bit about radicals and orbital effects. And this is where radicals, as they're electron deficient, behave very differently than anions. So radicals are electron deficient species and are destabilized the closer they are to the nucleus. Remember, we don't want positive charges close together. Increasing S character results in a shorter orbital that is closer to the nucleus. And if our orbital is closer to the nucleus, our poor radical, which is already electron deficient, is going to be destabilized. So, in other words, the more S character, the less stable your radical is. The less S character, the more stable your radical is. So if we compare an sp to an sp2 to an sp3 carbon, the more S character your carbon has, the closer your orbital is to the nucleus and the less stable your radical is. Does that make sense to everyone? This is the opposite trend that we see for anions. This is the exact opposite for anions because radicals are electron deficient and they hate being close to the nucleus because they don't want to be jammed up next to a giant ball of positive charge. Now, by the same token, radicals also experience destabilization from inductive effects. So electron withdrawing groups destabilize our free radicals. So if we have an adjacent electron withdrawing group, that results in a less stable radical. Radicals are electron deficient, so they want to get electron density. They don't want to have something take electron density from the radical. Does that make sense so far? Is everyone comfortable with this idea? So we're going to start to apply, we're going to apply this idea, and we're going to indicate the lowest energy radical for each pair. I'm going to call the left row A, the right row B. So take a moment for this first problem and tell me whether A or B is the lowest energy radical. Let's tell me whether A or B for this first set is the lowest energy radical. Okay, I see a lot of people typing A. Yep, A is completely correct, and that's due to resonance effects. We can distribute our radical over a total of 7 atoms versus 3 on structure B. Okay, let's take a look at this next group, and I'd like you to tell me whether the chlorine radical or the bromine radical is the lowest energy radical. Which one's the lowest energy, A or B? Chlorine versus bromine. Which one's the lowest energy? I see a lot of people typing bromine. That's correct. Bromine is larger than chlorine. Remember, for atom effects, the larger your atom, the more stable your radical is on that atom. Okay, let's take a look at another pair. I'd like you to compare this next pair of atoms and tell me whether A or B is the lowest energy radical. A or B? The vanillic or the alkyl radical? And think carefully and take a moment to consider what is the hybridization of each of these atoms? What's the hybridization of each of these atoms? So take a moment. You may, if you want to revise your answer, you're more than welcome to. So let's compare now. This is an important one for discussion. So here we have our radical on an sp2 center, while here our radical is on a quote-unquote sp3 carbon. So since the sp3, the alkyl radical has less s character, that in turn leads to a more stable radical. So that's why answer B is correct. So this has to do with atom effects in terms of hybridization. Radicals prefer to be on atoms with the least amount of S character. That way they're farther from the nucleus and less destabilized by our nuclear charge. Does that make sense now? Is everyone comfortable with that now? It's just another trend of stability that you need to get familiar with. Okay, let's look at another set of pairs, and just like before, I'd like you to tell me whether A or B is the lowest energy radical for this first pair. So take a moment to type in chat and then we'll discuss. Let's try to get a few more responses in the chat, just so that way we can have a nice class discourse. Let's get about 1 to 2 more responses. So which one's the lowest energy radical, A or B? Yep, we are asked to identify the lowest energy radical, and everyone's correct in noting that it's A. If we compare tertiary to secondary, the tertiary is more stable. More stable due to hyperconjugation. Okay, let's compare this next pair. Let's compare this next pair right here. I'd like you to tell me whether A or B is the lower energy radical. So take a moment to think through this problem, and then we'll discuss in about a minute. So I see a few people typing B. That's perfectly correct. So in terms of electron withdrawing effects, nitrogen has a weaker electron withdrawing effect and a stronger donating effect. Yep, so B is perfectly correct. Let's look at another question. So let's compare A and B for this next pair, and take a moment and indicate which radical is more stable, A or B. Let's try to get a few responses in the chat before we discuss. Let's try to get about 1 to 2 more responses before we talk about this. See a lot of people typing B, and that's perfectly correct. The bromine is a weaker electron withdrawing group. And because of that, it's less destabilizing for our radical. Let's compare the next species, A and B, an alkoxy radical versus an alkyl radical. Which species is lower in energy? Which radical is lower in energy? See a lot of people typing B. That is correct. In terms of atom effects, carbon is less electronegative. And as a result, it's more readily able to stabilize the electron deficient radical. Perfect, perfect. Everyone's doing quite well so far. Are there any questions on this section in terms of trends for radical stability? Any questions so far? Okay, let's keep going. Let's stop here for today because we're not going to be able to address the topic linked to carbocation stability in the same lecture, and I want to make sure we touch on these points in this exact same lecture. So I'd like you to just get familiar with the slides on radical stability, as it's very similar to the trends for carbocation stability. So we'll stop here. This is as far as we'll go for the next exam. We'll resume lecture on Monday, and for the remaining lab time, I'll leave the time open for everyone to ask questions on the lab and ask questions on the lecture content.